Yes, good afternoon, everybody. Dear delegates and other invitees. Now we are starting the session, parallel technical session, 30th practical session between 2 p.m. to 3:25. We have three lectures. One is state of practice lecture by distinguished Professor Satyendra Mittal, I.I.T. Roorkee, and special lecture by Professor Prishati Chaudhary from IIT Kanpur, and another special lecture by Professor Pijush from NIT Patna. And in this session, we have distinguished chair and the co-chair. The session will be chaired by Professor Shivapriya Mukherjee, and the co-chair is Dr. Saha Dubhaji from Bata Atomic Research Center. Sir, on behalf of the organizing committee, I welcome all of you to this technical parallel session 30th. So it is my privilege and honor to introduce our chair on this occasion for the August delegates. I will share my screen. Yes. So it is my pleasure to introduce Shivapriya Mukherjee, who is chairing the technical session. Dr. Mukherjee is a professor in civil engineering at Jadavpur University. He obtained Bachelor of Engineering, Civil Engineering and Master of Civil Engineering degrees in 1978 and 1981 respectively from Jadavpur University, and PhD from IIT Kharagpur later in 1997. He went to National University of Singapore in 2005 as a visiting professor. Professor Mukherjee has supervised 15 PhD theses and more than 55 master's degrees theses. He has published more than 150 papers in international and national journals and conferences. Professor Mukherjee has efficiently managed various administrative roles, including serving as Dean of Faculty of Engineering at Jadavpur University. He also served as Chairman IGS Kolkata chapter. With this brief introduction to our audience, I wholeheartedly welcome Dr. Priya Mukherjee to conduct the session. Sir, welcome, sir. It is my pleasure to introduce our co-chair of the technical session 30th, Dr. Shah Sabuji, graduated from Jadavpur University, Kolkata in 1988 and joined one-year orientation course in nuclear engineering at BARC Training School in 1999. On completion of the course, he joined Baba Atomic Research Center, Mumbai in 2000. He completed his PhD from IIT Bombay in 2016 and is affiliated to Homi Bhabha National Institute, Mumbai. He has served Homi Bhabha Award. He received Homi Bhabha Award for securing first rank in civil discipline at BARC Training School in 1999. He has received Group Achievement Award from DIE in 2013. He has supervised 5 MTech students and is external examiner for MTech dissertations for University of Mumbai. His professional assignments include analysis and design of industrial and nuclear safety related structures, interpretation of soil investigation data, and interpretation of concrete NDT data. He is member of various task forces and safety review committees at BARC and Atomic Energy Regulatory Board, Mumbai. He is principal collaborator for an ongoing BRNS project with IIT Bombay. He also serves as reviewer for research projects submitted to BRNS. He has authored over 50 articles in various national and international journals, peer-reviewed conference proceedings, and book chapters also. So with this brief biodata, I welcome Dr. Saha Dubhaji to this session as a co-chair. Sir, on behalf of the organizing committee, I welcome you. Over to the chair.
Introduce the next speaker. Professor Pijush Shamui. Professor Pijush Shamui is working as an associate professor in civil engineering department at NIT Patna, India. He graduated in 2000 with his BTech degree in civil engineering from I.I.Sc Shivpur. He received his MSc in Geotechnical Earthquake Engineering from Indian Institute of Science, Bengaluru, India. In 2004, he holds a PhD in Geotechnical Earthquake Engineering in 2008 from I.I.Sc Bangalore. He was a postdoctoral fellow at University of Pittsburgh, USA during 2008 to 2009 and Tampere University of Technology, Finland, 2009 to 2010. In 2010, Dr. Pijush Shamui joined in the Center of Disaster Mitigation and Management at VIT University as an associate professor. He was promoted to full professor in 2012. Dr. Pijush is the recipient, Dr. Pijush Shamui is the recipient of the prestigious CIMO Fellowship in 2009 from Finland for his integrated research on the design of railway embankment. He was awarded Shamsher Prakash Research Award 2011 by I.I.T. Roorkee for his innovative research on the application of artificial intelligence in designing civil engineering structure. He was selected as the recipient of IGS Sardar Resham Singh Memorial Award in 2013 for his innovative research on infrastructure project. He was elected Fellow of International Congress of Disaster Management in 2010. He served as a guest in Disaster Advance Journal. He also serves as an editorial board member in several international journals. He has been selected as an adjunct professor at Ton Duc Thang University, Ho Chi Minh City, Vietnam. He has been visiting professor at Far East Federal University, Russia. So he is a very brilliant professor and research worker who has experience in innovative research. So with this brief introduction, I request Professor Pijush Shamui to start his lecture.
So I will try to give some new things about some interdisciplinary techniques in application in the geotechnical earthquake engineering. So it's not traditional field of the geotechnical engineering what we have talked. This is some interdisciplinary technique that I have applied in the field of geotechnical earthquake engineering. So the title of my lectures is Application of Soft Computing in Geotechnical Earthquake Engineering. So in this lecture, I will try to talk about various soft computing techniques, how it is applicability in the field of geotechnical earthquake engineering. So first, I will talk about the how to predict the soil liquefaction based on soft computing technique. Generally, we use seed and this approach and other approach also, but here I will use soft computing to predict whether soil will liquefy or not liquefy. So as we all know that generally soil failed due to the increase in pore water pressure. That's why it loses strength. So if you look at these two pictures, that all the buildings are structurally good, but due to the ground failure due to the liquefaction, the whole building has been tilted. So as a civil engineer, you have to know whether this soil is liquefable or not liquefable. Now, as liquefaction, as we know that generally we use different in situ test technique for the soil for determination of liquefaction of the soil. Generally, we use the cone penetration test (CPT) as well as standard penetration test and the multi-channel analysis of surface wave that give the salinity profile. So generally, these all tests generally used to determine the soil liquefaction for a particular place. Now, first technique I will use, that is called support vector machine. So what actually we are doing in this technique, basically if you see that liquefaction problem is basically a classification problem. That means you are there is a two class data is there. One, for example, this data is liquefiable soil and this data is non-liquefiable soil, and we want to classify the data between these two. That means this is the mixing. You have get maybe 100 data set, and there is some data is liquefiable and non-liquefiable data is also there. Now, how to classify this data set? So if you consider it a two-dimensional plane, that you can construct a plane here. So and then for the width between these two planes is called the margin width. This is called the margin width. As if you apply the common sense, and you can easily see that if the distance between these two planes is more, then it will be good. As a classifier, it will be good. So SVM tries to make that this distance between these two data set, liquidable and non-liquidable data set, should be more, and that's why SVM does that, maximize the margin, and these two classifier, this classifier and this classifier, has been given by some data set that is called on support vector. That means which is this close to this line, that is called a support vector, and that used only for the final prediction. Other data are not used. That means they're not using all data for the developing the model. They're only using few data for the final prediction. So that is the overall approach of the support vector machine technique, and these I have applied for the liquefaction problem. Now coming to the what we have got this motivation of this work. Actually, if you look at Whiteman 1971, he gave actually there is boundary between liquefaction observed and no liquefaction. If you plot soil parameter and earthquake load, so from that, if you come to the SVM actually, so there is a two data, no one data is liquefaction, another data is no liquefaction. So you can construct many planes, so many lines. So the question is that which line you will use for the final prediction. So as I have already told that it will use which is the maximize the margin, because if the data between these two is maximized, then obviously it will be good for the final prediction. So that technique is being used to determine whether soil is liquefiable or not liquefiable. Now coming to the liquefaction problem, it depends on the two parameter. As we know, one is the earthquake parameter and the soil parameter. So this is the input of the model, and model will give you the two output. One is the +1 and -1, where -1 means liquefaction and +1 means no liquefaction. So soil parameter, earthquake parameter is, as we already know, that is cyclic stress ratio, and determined by the well-known Seed and Idris approach by using this formula that is called the CSR. And the second point is that what is that our soil parameter. Soil parameter I have taken, as I have already told, that is cone resistance value. So if you come to the SVM, there is a there is a data set is there. So X is our input and Y is the output. So X is equal to, actually there is two data set. One is the cyclic stress ratio and QC, and Y is the whether soil will be liquefied or not liquefied. Now, the linear hyperplane has been constructed by this equation. So, and for these two classifier, we consider these two equation. W is the weight and B is the bias. So, if you combine these two equation, it will come this equation, and this is for the ideal condition. But there will be always some noisy data set will be there into the CSR and QC. So that's why SVM added one slack variable that is always should be greater than or equal to 0. So this is the overall this is the equation to get the final prediction. Now this is the soil parameter. We are getting the cone resistance value that is well known as a geotechnical. We all know that what is the compression test. I am not going to the details. So that gives the cone resistance value. That is the input of the my SVM model. Now, I have taken a data set from Chichi earthquake in 1999. Around 134 data has been used to develop the model. And data set contain information about the cone resistance, CSR, and peak ground acceleration, as well as status of soil. Status of soil means whether soil is liquefying or non liquefying. So that data has been divided into two parts. One is the training data set and testing data set. So what is the training data set? Training data set used to train the model. That means to tune the model to get the good performance. So always it will be more data set. And in this study, around 94 data has been used for the training data set. And testing data set used to verify the model. And this around 40 data has been used to verify the model. There's a radial basis function has been used as a kernel function that is required to develop the SVM model. Now, what is the SVM model? If you look at, there's a two parameters there. This is called tuning parameter. That is one is called C, capacity factor, that is 150. I have 150 giving the good result. Another one is the width of the radial basis function, that is equal to 1. So training performance and testing performance 100%. That means whatever data we have given, that correctly classified a whole data set. So as you see that we have used around 94 data set, but only number of properties is 3. That means only 3 data has been used for the final prediction. So what is the drawbacks of this model? One is that actually, if you look at the CPD data, does not give any soil sample. And if you look at the CSR equation, we require the gamma. Gamma means unit to the soil. So, but CPD does not give the soil sample. That's why we cannot use the only CPD data, CPD test for development of the model 1. So we have to do another test to take the soil sample. And that's why what I have done, I have developed another model. I have used only Max peak ground acceleration for the model 2. So model 2 actually I have used the peak ground acceleration and the QC value, and all other things remain the same. And here actually design value is sigma is equal to 1 and C is 100, and here number of parameters has been increased, and the performance almost same 100%. That means we have to not use CSR as a input parameter in the model 1. Only peak ground acceleration is sufficient to develop the model for prediction of the liquefaction on non-liquefable soil. Now coming to the equation, SVM is giving nicely equation is that S is equal to sine, this is a signum function, and I is equal to 1 to 94. That means this is the number of training data set. Alpha I, you take the value from this equation, from this graph. So when you take alpha is equal to 1, then you take this is the value of the alpha, and yi is the corresponding what is the output minus 1 or plus 1. Then if by using this equation, somebody can determine the value of the soil liquefaction. And so and performance of the training data set is almost 100% that I have already told. Now I have used some other data set that is not a Chichi earthquake data set from the different parts of the world, and out of 109 global data, and that only 97 data has been correctly classified, and remaining data has been not classified. So around 12 data has been misclassified. That means the developed model has the ability for predicting liquefaction of the soil. Now coming to this, after developing this model, I had to develop a chart between the liquefable and non-liquefable soil. So the chart is between QC and not CSR is the peak ground acceleration. So if you look at this, that we can tell that this zone is highly possible that soil will be liquefiable. So this is the one good thing that we do not need to calculate the value of the CSR. Now coming to the my second topic is called the landslide and slope failure. That depends on the different parameter of the slope angle, height of the slope, OSN, unit of the soil, pore water pressure coefficient, and angle of internal friction. So these are the all inputs for a particular slope, and the model will give you the output whether slope will fail or it will be the stable slope. So this is the same thing. Subautomated machine have been used over here also, and I have used input. Actually, this is the all our input, and the output is the two case fail slope or the stable slope. So that from that for development of the model data has been collected around the world. So 12 from Australia, 8 from UK, 8 from China, 6 from Canada, and 5 from India, 3 from USA, and 1 each from Japan, France, Spain, and Greece and Italy. So all data has been collected, and then the data has been divided into 2 parts, just like liquefaction problem training data set. Around 23 data has been.
Sorry to interrupt, Chairman sir. We are running short of time because our panel discussion has started. So please instruct the presenter to close early.
Okay, I request Mr. Professor Samui to kindly conclude the speech.
Within 5 minutes, I will conclude.
It was interrupted.
Yeah.
Sorry to interrupt.
Yeah. Okay, no problem, sir. So this is the training data set and testing data set. So this thing also same thing. They give the equation also. Now this equation can be used by the practitioner engineer to determine the stability of the slope. Now as the time progresses, I am just giving a new concept that is called nowadays people are using, that is called the big data. Big data means there's a huge amount of data. That means there is 4V is there in the big data. That is high volume of the data and variety of the data, and a velocity, that is the frequency of the data, and veracity, the quality of the data. So these 4V is governed by the big data. For example, if you collect all SPD data around the world, there will be a huge amount of data, and every day there will be some SPD data is going on all over the world. So that means every day data will come. So how to model this big data for in the geotechnical earthquake engineering problem? That will be very interesting result. And coming to this, there's recently one paper published by the Cortes et al. They have, using the big data concept, they have calculated the predicted the earthquake magnitude using the big data concept, and that is published in the Computer and Geoscience. So it will be very useful for the who wants to do in this field of research. Now, coming to the conclusion, actually, the performance of the soft computing is very much data specific. That means if this, you cannot tell that SBM is the best model you use for the all problem. It only after doing the modeling, you have to check the performance of the all model. Then only you can tell which model is the best. The result of the soft computing should be analyzed thoroughly, and decisions should be taken based on the practical experience. That means you cannot use the soft computing result blindly. You have to check, and that you have to visit the site, and you have to take in the based on your experience. And third thing is that it can reduce the cost of project, because obviously number of tests will decrease by using soft computing techniques. So automatically the project cost will reduce. So this is some of the published of my books. So if somebody interested of this technique, they can read this book. It is available in the Amazon also. This is my author profile. Thanks for kind attention. I try to finish as much as for early.
So thank you, Professor Shamui. It's a very nice lecture. Days of data analysis are coming. So I think this is also entering into the civil engineering field, and you have highlighted that you have started research on that. It is very good. Is there any question? Professor Shimui, can you see any question there?
No, sir, no question is there. Actually.
No question is there. So I have just one question. When you are considering the liquefaction data, then to CPT, then up to depth you are going.
Up to depth, I think around if you 10 to 12 meter. Whatever data we have, that is 10 to 12 meter.
Up to 10 to 12 meter, then it is okay. That's why I was asking. So anyway, if there is no question on the lecture of Professor Shimui, so we thank him very much for the lecture. And
you can email me also for your any inquiry or anything.
Yes. So I request co-chair Dr. Dauji Shah to kindly sum up the session.
Yes, as we are running short of time, this summary will also have to be very short. Well, during the start of the session, we heard from Professor Satyendra Mittal about designing new railway tracks in India for the high-speed trains, which is one of the flagship projects of our present government, and how we can incorporate the expertise provided in international codes into our national railways, that he has explained very nicely. And he has also suggested that this should be explored for national highways as well. And that is a very good take-home information from his lecture. Thank you, sir. In the second lecture, we had Professor Prishati Raichaudhuri telling us about the rocking shallow foundation, how we can have the benefits of reduction in the demand in the structure, reduction in deformation in the structure, and how we have to balance with the settlement, sliding and rocking effects which is observed in the foundation when we go for this sort of rocking shallow foundation. And we have also learned about how geogrids, both natural and synthetic, how they can be used to reduce the settlements particularly. They are not reducing the rocking or sliding motions. And we have also understood how a lot of new research is required for standardizing the process of designing this sort of geogrids for rocking shallow foundation. In the last lecture, we had an expert in soft computing and big data analysis, Professor Pijush from NIT Patna. Actually, his number of books, which he has given a glimpse, tells us about his expertise in this field. He has given us some glimpses of application of soft computing in the field of liquefaction, slope stability, and also he has given us some indication of how big data can be really useful for site characterization as well as solving geotechnical problems with economy and speed. So with that, I would close the summary of the session number 30, and I hand over the podium to Professor Mukherjee for final concluding remarks. Please, sir.
Thank you, Dr. Shah. So it is really my pleasure. It was really my pleasure to chair the session. I thank the organizers for giving me this honor. And with this, I hand over the virtual microphone to the organizer, to Dr. Raju, for formally closing the session.
Thank you, sir. I'm extremely sorry, due to the constraint of time, we are forced to put pressure on the speakers because our one of the event panel discussion is going to start right now at 3:30. So sorry for that. And I take this opportunity to thank the chair, Sivapriya Mukherjee, and the co-chair, Dr. Saha Dabuji, for wonderful management of the session. And on behalf of the organizing committee and on my personal behalf, I extend my sincere thanks to one and all you for having made it possible in spite of your busy schedule. Sir, I thank you very much on behalf of the organizing committee. At the same time, I thank personally as well as on behalf of the organizing committee the distinguished speakers of this session, Professor Satyendra Mittal, Professor Rishatri Chaudhary, and Professor Pijush for delivering excellent lecture on this occasion. So thank you one and all. So please join the panel discussion, madam, and followed by this valedictory ceremony.
Okay, thank you very much, Mr. Govindra.
Thank you, madam.
Thanks.
Thank you.
Okay,
Thank you very much. Thank you all.
bye. Thank you. Bye.